Morning, everyone. My name is Chao. I just finished my PhD from the University of Kansas under the supervision of Dr. Huan, and I'm joining University of Wyoming as an assistant professor at the end of this month. So I'll talk about this fairness part on a safe data analytics. So here's the outline of the talk. It's actually very simply structured. So we talk about introduce the background and give some motivating examples. And after that, we talk about some notions that are related to fairness. And finally, we try to, review the literature on fairness-aware machine learning, how people implement fairness. Okay, so the background here is that is machine learning and data mining, of course, they're widely applied, increasingly applied actually in many consequential decision makings. Okay, so such as jurisdiction or policing or recruitment and also advertisement. And now, because of this increasing application, now algorithms are holding more accountabilities for the decision fairness. Now, in the old times, people ask, people question that whether the human employment has some human employment practice has bias, but now they ask whether the algorithm employment practice has bias. Here's one example on recidivism prediction, which Professor Huan actually mentioned earlier. Xiaoli also mentioned this earlier. So basically, in the court that. Machine learning is applied to predict the probability for a defendant to commit a crime in future, and this score will be used as a reference. And Compass is a widely used algorithm in the court to predict the recidivism. And recent study shows that Compass prediction has some racial bias. And to be more specific, the Compass will mispredict a group of people. A group of actually innocent people to have higher risk of committing a crime in future, and among these people, most of them are black. And on the other hand, Compass mispredicts a group of people, group of criminals, as low risk, as having low risk of committing a crime in the future. Among these people, most of them are white. So the racial bias here is very obvious. Another example is in face recognition. So face recognition is widely applied, in surveillance, and there was a study actually conducted by an FBI agent showing that the commercial algorithms have, racial bias too. And to be more specific, the algorithm makes higher prediction errors on black people. And so if you look at the curve here, that given the, I should use the laser, which is not working.
On the side it's on and off.
Oh. Okay, it's okay. Right. So if you look at the figure here, so given the same false acceptance rate, actually the true acceptance rate for black people is significantly lower than other people, and then non-black people. And this means that if we apply face recognition as an entrance system, then the system will more often reject those authorized black employees. The first question people ask is how can an algorithm, a common question that people ask is how can algorithm be unfair? I mean, the most common reason is that those algorithms they may inherent human bias embedded in the training set. Another reason is that they may amplify those bias in the observations. Now, it is okay if we have some observation bias, but it is very dangerous for the algorithms to learn those bias as part of his decision rules. If you're more interested in this, fairness, aware machine learning, there's a growing community called FAT machine learning, which stands for fairness, accountability, and transparency, and it has annual workshops. So, and there are a lot of resources on its website. And actually, I think this workshop is this year is in conjunction with the KDD, which will be on Monday, I think. Okay. So, and now we talk about how people can characterize fairness. So what we try to do here is to characterize fairness from a legal perspective using the legal notions. So there are two popular notions. One is called disparate treatment. Another is called disparate impact. Okay, so roughly speaking, disparate treatment means that the decision process should be fair. Okay, meaning that the decision, one's decision should not be based on those protected attributes such as age or gender or race. And disparate treatment actually encourages fairness at the individual level. So equally qualified, candidates should receive, equal decisions. Another notion is called disparate impact, which basically says that, the decision results should be balanced between the minority group and non-minority groups. Okay, we'll give a bit more specific definition later, but in general, disparate impact encourages fairness at the group level. Okay, so two groups should have balanced the decision results. And so then we inspect, we surveyed the literature. We did some survey on the literature of fairness aware machine learning, and we tried to, categorize the existing works, in a legal dimension, based on whether they are trying to mitigate disparate treatment or mitigate disparate impact. And here, the horizontal axis is another dimension, which we can be considered as a technical dimension to characterize the literature. And it is actually it was proposed in last year's KDD tutorial, and it's a very nice dimension. So whether they are those methods are pre-processing methods or in-processing methods or post-processing methods. So and then if we combine our dimension with them, we can categorize the literature into 6 groups and. Okay, so so basically in the following, what I'm going to do is I'm going to briefly overview each category, and then elaborate one or two example methods. Okay. So to introduce some notations, we assume there's a population X, usually a set of candidates, a set of applicants to a position, and then there's a label set Y. Which we assume is binary, just to simplify discussion. So either accept the applicant or reject the applicant. And then we assume there's a protected attribute. There's just one, we assume, which is also binary. So this attribute could be gender, okay, or race or age. And then we assume that the positive label represents advantage predictions. By advantage prediction, I mean accept the applicant. Okay, by disadvantage, I mean reject the applicant. Okay, and then we assume there's a predictive model F from X to Y as usual, and then we assume there's a partition of the population based on these protected attributes into 2 groups. Okay, X1 and X2, and of course we call one group, either one of them as minority group if the group is receiving discriminated predictions. Okay, and the other group as non-minority group. Okay, and of course, the whole point of us doing this fairness-aware machine learning is to study whether there is some discriminations, between the predictions on these 2 groups. So we start from pre-processing method for to mitigate disparate treatment. Okay, so the general strategy is to discover and correct some unfair labels, individual labels in the training sample, and then correct them, and then perform standard learning. And the hope is that by correcting these unfair labels, then our learned model will give fair predictions. Of course, how do we know a label of an example is fair? So the current method, they assume that if the labels of similar examples have bias against the minority, then the label of this X is likely to be unfair. Okay, because if there's a bias, on the neighbor's predictions, that means the decision process within this neighborhood is probably unfair. So the label on X is probably unfair. We'll get into more detail in the example. Okay, and of course the current methods they use different attributes to measure the similarity. So, how do we know which examples are different? So, one method uses all attributes. Another method published in last year's IGCI, they use attributes with direct cause on decisions. And then here the cause is, the notion of cause is based on the causal Bayesian network. So here's one example method. Okay, so how do they decide, whether a label is unfair? So they say the label y of x is unfair if it is a disadvantaged label first, and if x is a minority candidate, and the third one is that if the neighbors of x have some so-called t-discriminated labels. Okay, and this notion means a metric, this x is greater than t, where this matrix is equal to the difference, between two probabilities. Okay, so the probabilities for minority neighbors and non-minority neighbors to receive disadvantaged decisions. Okay, so this difference is if this difference is greater than t, then we say the neighbors of x have t-discriminant labels. Okay, and then after they detected, after they decided the label is fair, then they flip the label. Okay, if it's rejected, then they flip it to be acceptance. Okay, and then perform standard learning. So here's the result. So they set this value t to be 0.1, and they run experiments of different classifiers on the dataset without correcting those unfair labels, and on the dataset with after correcting the unfair labels. So the discovery is that the accuracies of all the algorithms they decrease slightly, but in the meantime the discrimination of those models decreases significantly. So it is suggesting that by removing the fairness, by removing the bias in the dataset. Yes.
So I noticed that as the accuracies fall, maybe you'll get to it. Is there any characterization at all of where those new errors fall? Do they fall uniformly across all the whole population, or do they fall in some biased way?
Wow, that's a very good question. I don't think that I don't recall they have this specific measure, but I think it's. Yeah, it will be very interesting to look into that. Yes, I do. Thank you. Any other questions? Wow. Awesome. Okay. Okay, I'll move to the next category then. Next category is how do people apply in-processing method to mitigate disparate treatment. Hey. Okay, this is not working. All right. So the general strategy is to add some constraints on the fair decision process, of fair decision process in the standard learning, in standard learning, and we categorize the current works based on whether the constraint is active or passive. Okay. By active we mean they specified what should be the predictions. Look like for similar candidates. Okay, so some methods they claim that similar candidates should have similar predictions. Some claim that superior candidates should have superior predictions. And this work is studied in the context of bandit learning. Okay, so by superior candidates, they mean that the arms. Okay, maybe I should not elaborate this here. Okay, and for this passive by passive constraint, I mean they require that the predictions are statistically independent to the protected attributes. Okay, they have measures for that, and if we have time, I will elaborate that. So I move to okay. Now I elaborate one example on this active constraint for fairness. So it is done by Dr. Tinta Dwork, and I think she has a keynote at KDD on Wednesday all about what is fair. That would also be a very interesting talk if you're interested. So the claim is that a model is fair. The argument is that if a model is fair if it is Lipschitz continuous. Okay, so here the F is the model as you recall, and X and Y are two examples in the population. And here, the capital letter D and small letter d, they're just proper metrics. Okay, proper metrics. And of course, in the study, it is assumed that the range of this function f is a set of distributions. Okay, so the output is a distribution over the label set. So it is more general than the common deterministic setting where the output of model f is just a single value. Okay, so it's a distribution. So they claim that the model is fair if it's Lipschitz, meaning that if the two candidates x and y, they are very similar, the d is very small, then their predictions should be also very similar. Okay, meaning that the fx and fy should also be, this capital D should also be small. Okay, and then they add this constraint in the standard learning process, so which is formula here. So on the top, it is the standard loss, training loss. So it is the loss of x and its prediction y, where and its label y, I'm sorry, and where y is taken over the distributions, and then x is taken over the population. Okay, and then they add a constraint that for all the the pairs of examples, they should satisfy this inequality, Lipschitz inequality. Okay, and they show that this problem can be formalized as a linear programming problem, therefore can be solved easily. Yes.
What is the distance measure d used here?
Which one? Small d or capital D?
Small d.
That's a very good question. It is assumed in this study. It is assumed that a metric d is given. And it is assumed that this metric is fair. That means it can fairly measure the similarity between candidates.
That's the distance, the Euclidean distance is not fair for the images, right? Because two images have very low Euclidean distance. They may have the same label.
Okay. That may be. I haven't studied this problem yet. That may be the case. But in this study, they didn't go into detailed formulation of the metric because they stay at a theoretical level only. So, but yeah, that's a very interesting question. I think metric for image, yes. And then just for your information, the capital D, they use some F divergence to measure the difference between two distributions. Okay, so one interesting open question in this study. Well, at least I find it very interesting. Open question in this study is how in practice, how do we design a fair metric, right? So fair similarity metric, and actually it is a problem. It is open question to all the solutions to that try to mitigate disparate treatment, right? So and of course in this study it is assumed given by the domain experts, but and in most studies those metrics are handcrafted. In most algorithm studies, okay, are handcrafted. So is there any way we can, maybe learn a fair metric? That would be an interesting question. Okay, so all right, yeah, that's the end of the second work. Okay, the last work. How people apply this the post-processing method to mitigate disparate treatments. Okay, it is so far I've only found one. Probably there are more coming, but I just found one. So the general strategy is to first we perform standard machine learning. We learn the model, make predictions, and then they perturb these predictions, and hopefully the result will be fair. And by fair, it means that the perturbed result, YP tilt satisfy these two equalities, okay, which they call the equalized odds. Okay, so so here I'll just explain the first. Equality because the second is similar. So the equality means that if for the examples x from different groups, either group 1 or group 2, and if they are both unqualified, they're actually unqualified, then their chance of out of oh no, then their chance of receiving advantageous decisions should be the same. Okay, if they're truly unqualified, then their chance of receiving, advantageous decisions should be equal. And also for the second equality just means that if they're truly qualified, then their chance of receiving advantageous decisions should be equal. Okay. Questions? Okay. So right. So so basically in this study the decisions process is fair in a sense that, right? So equally qualified or unqualified people, they should have equal opportunities of probabilities of receiving advantageous predictions. So that's much. Okay. Yeah, that's all about the disparate treatment part, and actually more works have been done on the disparate impact part. So let's just see how people apply preprocessing techniques to mitigate disparate impact. Right. So just to give you a rough idea about what disparate impact means. Suppose recall we have partitioned the population to two groups, X1 and X2, and we say a model prediction has disparate impact between these two groups if the following two probabilities are significantly different. Okay, the probability is so basically it's the probability of for examples in different groups to receive advantageous predictions. Okay, if they're significantly different, and then there's disparate impact. But of course, there are different ways to measure the difference, right? You can measure the direct difference, or you can measure the ratio between them. Yes.
In this, do you also fold in the idea of disparate mistreatment? So that's something else that's been proposed as a third category from disparate impact and disparate treatment, is the idea of different misclassification rates depending on sensitive attributes. And so that's like the work of people at Max Planck Institute, for example, got work on disparate mistreatment and removing it.
Oh, really? I don't recall. Where did they publish the paper?
World Web Conference, they've been at most of the FATML workshops, right?
Yeah, those are their tomorrow. Yeah.
Oh, you'll be tomorrow?
Krishna Kumadi and Bilal.
Yeah, I think Bilal is.
Oh, okay. Well, I guess I haven't read that paper, but I'll read it. Is it in tomorrow's workshop?
Well, there's been in the last few years. I mean, there's just a whole stream of work on that, and it fits in similarly. They also have fairness constraints. So just
Okay.
mistreatment.
Okay. Oh, that's very interesting. Okay, maybe
Yeah.
Okay. Well, yeah, I assume if that is the case, then maybe we can add a third category in the statistical dimension. Probably that would be very interesting. Wow. Okay. Thank you. If more. Oh, okay. Thank you. All right. Yeah. After giving you an idea, then I'll start to elaborate an example method in this disparate, in this category. Let me overview the general idea first, of course. So the general strategy is to modify the training set because it's preprocessing method, and so that the decision result can be balanced. Okay, and then the people perform standard learning. Okay, and so we categorize the current method based on what aspects of data they're modifying. They try to modify the features. Some of them try to modify the labels. Some of them try to modify the sample size. Okay. This is more kind of tricky, but also very interesting. So let's see. Okay. So we'll elaborate one example on how people modify the features. It was published in ICML paper. ICML. I mean, so the idea is to learn a discrete latent feature space Z, and where the feature values, the feature value distributions are balanced between different groups. Okay. So. So to be more specific, the authors, they first try to learn from the population a latent space Z, and then learn a prediction model from Z mapping to Y. Okay, they do this jointly, so that's why we're not sure where to put this work, because this part is preprocessing and this part is in processing. So, and so anyway, they try to learn such a latent space Z, which satisfy this equality. Okay, this equality means that the distributions of Z, in different groups, taking expectation over different groups are the same. okay? And they hope that the model learned from this balanced, group balanced, latent feature space can also give you balanced results, okay? And that's the hope. But of course, in the meantime, they have some other, standard constraints when they learn the latent space, right? The constraint is of course, the latent space have to be able to accurately recover, the original space. Oh, sorry.
In practical terms, how is that different from the equality of opportunity constraint that you talked about a couple slides ago as a post-processing method? The more
disparate treatment part. Yes. Let me think. That's a good question. Which one?
Right, the more Sparks work is further on.
For their own or
Yeah,
more previous?
forward. Yeah.
Okay.
No, the other way.
This one?
No,
For
further.
the future.
Yeah. Here, yes, this.
This one.
Right. So these constraints are substantially similar to the other than the expectation, and so I'm curious in practical terms how different does do the models behave?
Yes. Thank you. That's a very good question. I was actually also kind of confused about this one when I said the category. The difference is that here. Oh, right. Here's the laser. The difference is here they have an additional condition on different groups. So here is you can think of this as no disparate impact within truly qualified groups or truly unqualified groups. And the authors interpreted this as a fair decision process because truly qualified people have the same probabilities of receiving the email. And that one, this equality is linked directly to the notion of disparate impact. So and the authors they also claim that disparate impact. So but yeah, yes, and but yeah, personally I'm also struggling where to put this, I guess.
Is it the case that if the mapping to the latent space is perfectly faithful to people's actual classification, then these things are reduced to each other?
Perfectly.
If you imagine like a perfect mapping of test vectors into a latent space that understands what their true classification should be, then
Okay.
right, there's a lot of in the Hart paper. There's a lot of discussion about a theoretical perfect predictor, someone who has oracle access to the true answer.
I haven't thought about this question before. I think basically what you're suggesting is whether it's possible that this condition can be removed when
Well, I think
and
I'm
the
asking
mapping
if,
is.
like, in the latent space Z, if that condition is satisfied, are these in fact the same condition? Doesn't really matter.
Oh, if this equality is satisfied, whether it implies the previous equality. Wow. I don't know.
Yeah, previously the quality
I see what you're saying.
of the expectation.
I don't know, but I think it might be possible. I don't know. Sorry. It also depends on the distribution. So,
Yeah.
right, it depends on distribution. Okay, so right, so their hope here is that back to this. So their hope here is that once they learn a fair latent space, and they learn and then they can learn a fair model based on this space. Okay, so the hope is that, and they run some experiments, and it shows it is indeed the case. Okay, so they run their models on this credit data set where people try to predict dependability of one's credit, and they run a couple algorithms. So LR represents the standard logistic regression model without any fairness constraint, and there's a fair naive Bayes model proposed in earlier work, and there's another fair logistic regression model that they actually proposed in this work. And then finally, the LFR is actually their proposed method. So what they show here is that the accuracy of the model of the proposed their proposed model is slightly lower than slightly lower than other models, but their discrimination is significantly lower than the other models. Okay. Okay, it's time to be a little bit unfair here. So, so an interesting point in this work. Interesting point in this work is they run an experiment that introduces an interaction between the fairness and transfer learning. So what they showed here is that the fair feature space Z that they learned from one task can be applied to another, a similar task, and it also improves the prediction fairness for the other task. Okay, so that's the result they have, and then what? Oh, so what am I supposed to do? Okay, I should just speed up, right? Right, that's our reminding.
Go ahead.
Okay, well, thank you. Thank you. Right, so and then we run another, we find this result very interesting, because the interaction hasn't been studied, extensively. So we run some, other experiments, experiments in other transfer learning settings, and we found a different conclusion. Okay, we found that, this standard transfer learning, they can improve prediction accuracy as usual. Okay, as usual, but in the meantime, they will hurt the prediction fairness. Okay, of those target tasks, and we call this phenomenon discriminatory transfer. Just give a name. There used to, yes, there is. It has been widely argued that there is.
Argued to be, but not kind of rigorous, not much rigorous. There are.
I mean, many studies have shown empirical evidence that there is trade-off between in a single task. If you improve fairness, then the accuracy will decrease. So they have shown this. But the trade-off between this transfer learning, the accuracy improvement from transfer learning and fairness is unstudied. Does that make sense? Yeah. Thank you. So yeah, just to elaborate our experimental setting a little bit more. 2 more slides. So we run some data set, community crime data set where people try to predict the crime rates of communities. We simulate 2 tasks. A source task is to predict the crime rate for low-income communities, and of course we partition the original communities into low-income and high-income based on the, by just thresholding their income values, and then the target task is to predict the crime rate for high-income communities. And then we examine the algorithm, a very popular transfer learning algorithm called hypothesis transfer. And our goal, of course, is to examine whether there is discrimination in the predictions, against the black community. The fairness issue here is the black community against the non-black community, and so in the target task. So here's just representative results of our study. So the left figure shows the prediction accuracy in the target task, and the right figure shows the prediction fairness as measured by the equalized odds ratio and disparate impact in the target task. And as we can see, and then the x-axis is the value of lambda, which is a coefficient controlling the degree of information transfer from the source task to target task. If you increase lambda, then you transfer more information. So then in the left figure, you see that if we properly increase the value of lambda, then the prediction accuracy in the target task does improve. Okay, so this is the well-known benefits of traditional transfer learning. Okay, and of course, if you increase it too much, and then the performance may decrease. That may be due to what they call the negative transfer problem. But in the meantime, when the prediction accuracy is increasing, the prediction fairness is actually decreasing. Okay, so this is what we call this. So this part is what we call the discriminatory transfer. And we actually also have a poster at the workshop, the FAT workshop, so about this work. So if you're interested, feel free to stop by. Okay.
Did you
Yeah.
partition randomly? Did you also try just a transfer learning task with
I tried force a transfer.
one that didn't partition on a particular characteristic, and one that instead just partitioned randomly?
Partition the community?
Yeah, so you obviously you split communities up.
Yes.
And then you take down one task and you move forever. Have you split communities randomly?
Not randomly. I select 4 attributes and based on them to split the communities.
But did you also then? But you didn't go random one as well to see.
I also examined other cases, but I mean, in other cases, I did not observe any discriminatory transfer.
Right. Okay.
Makes sense. Okay, so yeah, that's end of our to do our own work. So how much time do I have now?
Now 11,
11?
plenty of time.
Oh, okay, I'm not sure. Yeah, okay, if I have plenty of time, I will elaborate another example method for this, another, I think, preprocessing method to mitigate disparate impact. So it was published in last year's KDD. So basically, in this method, the idea is to correct the feature values in the training set, and then perform standard learning. Okay, so the goal is to correct the feature values so that the resulted distribution, the feature distribution for different groups are equal. Okay, so in this this is a sample distribution. So this figure shows sample distribution, and the red curve shows the distribution for the first group. You can say minority group. And the blue curve shows the sample distribution for the second group, non-minority group. So they're different. Now, because they're different, the authors argue that people can infer the group membership of an example and make some discriminatory predictions or decisions. So what they want to do is to reduce this difference. So they try to merge the distribution. Okay, so that's what they try to do. And so I just because this algorithm is really interesting, I just try to elaborate a bit more. So this is what they do. Okay, so the blue curve and the green curve represents the CDF of different groups. So they're different at the beginning. Okay, and so this is how the algorithm modified the distribution of the blue curve. So they first found the feature value. And they, based on the feature value, they found the CDF value. And then they shifted this CDF value to the median of the, of the two groups, CDF values. So they shift it to the median, and then they map it back. Okay, map it back. So what I have, so basically they try to map, they correct the original feature value here to the new feature value here. Okay. And then they did the same thing for the CDF of the second group, of another group. Again, they start from a feature value here, map it to CDF, take median, and map it back. Okay, so by this means, both feature values, they're mapped to the same place. And this mapping does not change the rank of the feature values, in the new CDF. So that's what they claimed as rank preserving property, I believe. Okay, and then they run some experiments again. So the experiment they run is they first corrected these the distributions, and they perform standard machine learning. Okay, so here the the x-axis represents the disparate impact, which is a measure of unfairness. I'm sorry, and then and the y-axis is the prediction error. Okay, I'm sorry, I kind of forget. Embarrassing. I believe this is this part is the corrected result. So the corrected result shows that they after the modification of the feature value, and the prediction, the disparate impact in the model predictions is decreased, but the prediction error is increased. So Yeah, I believe that's so. Sorry, but basically this figure is another evidence of the trade-off between the prediction fairness and the prediction accuracy. Okay, so yeah, so those are two example methods in the preprocessing category, and then we'll quickly go over the last two categories. So it's in-processing method to mitigate a disparate impact. So again, the general strategy is to penalize disparate impact in the standard learning process. And of course, this disparate impact can be measured from one direction, meaning that one group's advantage decision rate should not be higher than the other group, or from both directions. Okay, so neither group should have higher advantage decision rates. And of course, in the second case, the constraint is more difficult to be optimized. So basically, in these studies, the authors they propose some approximate measure of this disparate impact, and then how to do optimization. That's sort of the point of the research here. And oh, I forgot. Yeah. So I'll elaborate the first one. Just give you an idea. So here's how they measure the disparate impact. So they consider linear regression models. And the parameters like W, the regression coefficient vector. And then here W prime means the transpose. Okay, so W prime times X just means the prediction on X. Okay, so the prediction on X in the first group and the predictions on X in the second group, those prediction values should be similar. The average values should be similar. So that's how they measure disparate impact. And you can consider this as a empirical empirical estimate of those the difference between two probabilities that I just showed you before. So this is the measure of disparate impact, and they add this measure in the standard learning process. So the first so this is the optimization problem, the basic optimization problem they formalized. So they have a standard training loss, and then plus this disparate impact measure, and so they try to minimize this difference. You have a question? No. Okay. Right. Another interesting point I want to bring up here is that some people argue that not all disparate impact are bad. Okay. Some of them actually can be explained. Okay. Then they call this explainable disparate impact, which is kind of interesting. Okay. So actually there was a case in the law. So many years ago, UC Berkeley, they were accused of having gender discrimination in their graduate admissions. There were people complaining that you take in more boys than girls, but then the professors from the university they try to defend their and then so eventually they discovered that yes, at the university level there's a disparate impact, but at the department level there's no disparate impact, meaning that within the department there's no significant gender bias, okay, against female applicants. Okay, actually some departments they favor female applicants. So yeah, this is a very interesting point. So then some researchers they propose to study this explainable disparate impact. So they assume that there are some attributes that can explain the disparate impact. So and then they say we should only penalize those disparate impact within each explainable set. So in the previous example, it would be we should only penalize disparate impact within each department instead of at the university level. So that's what they do. So yes, and of course based on this argument, they build they propose new penalization constraint penalization terms, and here are some results they obtained. So the OLS is the M is the model that they proposed that are learned on within each department, say in the context of that graduate admission within each department, and SEM is the model that they proposed. SEM is the proposed model. The OLSM model is the standard machine learning model without any fairness constraint that applied to each department. And then SEMM model is their proposed model that, learn least square, but with fairness constraint within each department. And then SEMMP is their proposed model with fairness constraint, just a single model, for all the departments. Okay, so if you look at the figure here, again, the left figure shows the discrimination, and the right figure shows the regression errors. And as you can see that, the regression errors does not decrease too significantly, while the discrimination decreased, right, based on their proposed model for all stratum and per stratum. Okay, last category. So how do people apply post-processing? So the idea is actually very simple. So again, you perform standard machine learning, you get a model, then you have a decision boundary for the model, right? Then basically the general strategy is to shift that decision boundary. You push that towards the minority community, towards the non-minority community, to mitigate disparate impact. Okay, so and there are different methods. There are different methods that some of them are pushing the boundary for particular models, the naive Bayes or decision tree, kind of ad hoc. There's another more general strategy to push the decision boundary for if the model can give you a prediction confidence. No, okay, I'll just let you done. Oh, okay. All right, take a picture. Okay, so I'll just briefly explain how does this general decision boundary shift method works. So I assume that the machine learning model can give a prediction confidence on any input example X. And so for the standard model, the threshold will be 0, meaning that if the confidence is above 0, then the prediction will be positive. Otherwise, it will be negative. And for the shifted model, proposed in this paper, the Fisher's paper, this threshold is no longer 0. It's actually a lambda. So if X is a minority, then the threshold is pushed to negative lambda. So even if you're not so including more minority people in the positive class, right? And then for the non-minority, the threshold remain the same. So that's how they push the boundary. So that's all about. Yeah, that's all about the works that we we covered in this tutorial. And of course, there's still many works being published. Actually, this year KD also has many works, and the Fed Machine Learning Workshop has a lot of new works we haven't have enough time to cover. But basically, one thing I want to emphasize here is our initiative here is to try to inspect the literature from a legal perspective, because right now, I think an ongoing discussion is, how do we characterize fairness? What do we mean by fair? And of course, as a technical community, as I recall, that we also try to propose some methods to characterize fairness. But I think it's perhaps it's more helpful if we base our characterization on some of the legal notions like disparate treatment or disparate impact, so that the research won't diverge too much eventually. So that's the whole point. That's why we propose this second dimension, legal dimension. So hopefully, but of course there might be a third characterization too, like beyond disparate impact or disparate treatment. But the point is, we have some legal dimension to inspect the literature. That might be more helpful. So then we review some of the methods in each category, and there's some future research direction too, like how do we find a fair metric, right? So what can we do with explainable disparate impacts, and also some of the questions the audience just asked. Those are very interesting questions. So yeah, that concludes my parts, and there's some reference, of course. And yeah, that's all. That's the end of this part. Thank you very much.